Alright, you finished? I think I am. Wait, I want you to test the slides. I'm sure you have something to do before me, and then check the slides of the future.
You still need that key store topic. It was Benjamin when we were discussing it. Yeah, so you were saying that it would be nice to. Did you have time?
Yeah, we have time. How did it?
10 minutes.
Yes.
Okay.
Hi, John.
Good.
You gonna sit here on these two?
Yes.
Can we plug you into the projection?
No, because we're not using my laptop. Where's my colleague? I don't know. He's coming, but he's not here.
Cool. No worries. Thank you.
Anyway, let me know if the slides.
I'm looking right now. Well, we actually did tell him you could have 10 minutes. We have to take a look. Your slides are okay. Well, Chrome is freaking out right now.
Fine, I guess. Okay, go quickly.
Yeah, that's good. Hi. How are you?
Yeah, see you. The meeting hasn't come yet.
Yes.
I have to go to another meeting, another session. I haven't sent my application yet, but I do.
Yeah, sure.
Do you expect people to draw?
I mean, ordinarily do, but is there someone else you can come drop? Okay, well, then I guess we'll do without. Okay.
I'll put together some words.
Okay, thank you. Not yet. I'm not sure where he is.
Okay, he's responsible for it, right?
No, I am.
You are?
Mm-hmm.
Okay.
It's me.
Okay.
Thank you.
Howdy.
Let's see, like. Hi, we're going to start in just a minute. I'm not sure where Ben is, but we'll figure it out. Oh, there he is. Okay, no problem. You want to plug in? Medium? Thank you, sir. So these don't say Tales from 23? Oh, sleep. Okay, cool. I'm uploading the slides now, or the rest of the slides. Okay, can people please take their seats?
I was just waiting for the Wi-Fi to switch.
Hi. For okay. Okay, I didn't know it was him. I thought it was Stuart. So
Sorry, Stuart.
Okay,
Very good. I just walked the ball on this.
that's fine. Okay, well, either one of you fine. You're saying this projector?
Yeah.
What's really old? I'm not sure what she's about.
We can just go through these other slides if you want. We have to make it work eventually. But. Well, if that one's correct, presumably this one being bad is not a problem.
Do you want to be on the mirror or on the extended display?
I'm set on extended right now, but I may have to mirror.
You're good, huh?
Yeah, good.
Just so you know, you're still 69, so if you know, just wait and 60 and go outside the screen.
So what are my options?
They're going to be 69. Just lower resolution, so you
Yeah.
show play. Just hold option. Scare. More options.
Thank you. Better. Thank you.
And then, so you do want to stay on extended, right? Oh, then mirror.
Yeah, there it is.
Yeah. Cool.
All right.
Are you
Is
on?
this live?
No. Hello? Okay. So this is SAG.
Sorry about the technical difficulties.
If this is not the flight you intend to be on, you will probably wish to deboard now. We're your hosts, Eric Rascola
And Ben Kaduk. And before we get started, I'm a new face up here, and we want to say thank you to the old face who has been a great AD for the past several years. So Kathleen, come up. We got you a couple things. So now that you have some more free time, you won't be reading drafts. So maybe we'll have some light reading material.
War and Peace.
Yeah, War and Peace. And you know, it might take you a little bit of time to get through that. So to keep Jude occupied.
This is a Wednesday.
Yeah. Well,
Tell us about 400 pages.
maybe this will buy you some free time from.
Is
Sun.
it the original Russian edition?
That might take 2 Wednesdays.
And if you want the bag, I have the bag
Thank you.
too.
Yes, and I wanted to say thank you. Yeah, and I want to say thank you, Kathleen, for really helping me get up to speed and, you know, making me the area director I am today. Seriously, thank you.
So it's Thursday. This is Note Well. You've probably seen it before, but Note Well. And here we got the agenda for this session. So does anyone want to bash the agenda? Looks like no. I have my table on my other laptop. So many working groups sent their reports in already. If you did not send in your report already, we're going to call you up. Do you want to call you up after that?
Yeah. I can also call the SAG agenda and see what's here.
Now this mic is live.
You want to just click through? Or you? So, yes, Ace, I hope you did that, Ben.
Jim did that actually. But,
Okay,
but
we
yeah,
have Ace, Acme.
Acme. We have Curdle. Dots. Do we get dots? Yes, we got dots. We got Emu. Got I2NSF. Got IPsectMe. Got Kitten, which I also did not do. Lamps. Do we get lamps in the past couple hours?
Maybe tomorrow.
Anything interesting? They meet tomorrow for those who need the microphone. Is Russ even in the room? Maybe he also found a restaurant that was slow to deliver lunch. Mile. Anything from Mile?
Yeah, we have something.
Okay. OAuth, we got Sackham met just before lunch.
We have a report.
I think that's everything then, because we got Sec Dispatch, Sec Event, not meeting yet, Suit, TEEP, TLS, very long report from TLS. Related work groups.
Does anyone from one of these want to get up and give us a short report?
Alexei Melnikov, CFRG met on Monday. We had a pretty full session. 4 documents are ready for IRSG review, like Argon and hash-based signature and rekeying. And we had some very interesting presentations on formal method of verifying correctness of security implementations, randomness improvements, and hashing to elliptic curve.
I'm not seeing anyone else jumping up to the mic, so I think we'll keep going. MLS BOF is later today.
It's later today in Birmingham. It's right after the session, actually. Come one, come all. We can talk about securing, developing a message security layer that can be used by apps, using some cool stuff with trees, racket trees, Merkle trees, all kinds of trees. Come.
All right, so now it's time for presentations.
So our first presentation is from Karthik Bhargavan, who's done like a lot of really amazing work on TLS and verifying protocols. I'm supposed to say that anyway, but I've worked with Karthik quite a bit, and it really is amazing. So he will amaze you.
Well, thank you, Eric. Thank you for the opportunity to speak to this lovely crowd. Slides are somewhere. I can talk about deprecating MD5 if you like, but yeah, the other one is better.
You should. That's what we're doing, by the way. My capsule.
Yeah, let's do that.
All right. So I was asked to talk a little bit about protocol verification tools, how they can be applied to various protocols that we are standardizing in this, the IETF and other places. So many of you have been involved in, or at least are aware of, what I call the TLS-1.3 experiment, where for several years, the TLS working group engaged in a collaboration with a bunch of group of academic researchers. And the idea was to do hand-in-hand, say, formal security analysis of the protocol while it was being designed and specified. So there's a list of, it's an incomplete list of papers I'm citing there. So as for every significant draft of TLS-1.3, there was usually some cryptographic analysis, some security analysis of various kinds, and various papers were published. So this was very productive for researchers because you got a lot of papers out of this at top venues. And I'm hoping it's also a good thing for TLS-1.3 because we can have more confidence in the final version of this RFC. So for those of you who are not really deeply into the TLS working group and how this whole thing went, you might be curious about some things like, well, there are so many papers out there. You say there are many analyses. Well, what do they all prove? How are they different? How much work did it take? And is it too much work? And for example, if you have a shiny new protocol, well, can we do the same thing for that protocol? So in particular, we are trying to do the same kind of thing for the MLS protocol you'll be seeing in the BOF later today. But you want to see how this kind of, I'm going to give you a little bit of a flavor. I was told for a 20-minute talk, so I'm going to speak for 20 minutes, and we'll see whether we can answer some of these questions. Next slide, please. Well, before the what and the how of these various verification techniques, it's good to remember why. Next slide, please. So for the 4 years before TLS-1.3 was designed, this is sort of what TLS was known for some reason, just because there were lots of these keyword-based attacks with nice web pages, logos, and news articles. And next slide, please. And if you kind of go deeper into these attacks, well, the first, you'll see a bunch of them were what I would call cryptographic weaknesses, which means that certain modes of TLS or certain modes of certain versions of TLS were known to be or were found to be not satisfying the cryptographic security that we expected from the protocol. Next slide, please. Another category of these attacks were what I would call protocol flaws, where the crypto was okay, but the way the various modes and features and mechanisms in the protocol were composed left some unexpected interactions, which again caused certain breakages or certain properties you might have expected to hold. Next slide, please. And the last category is implementation bugs, which sort of feels like, well, of course, any piece of software can have implementation bugs. But next slide, please. It turns out that often a lot of the attacks that became famous were relying on a combination of all of these. So there were implementation bugs, crypto weaknesses, protocol flows, all coming together in some kind of perfect storm to create all these attacks. Next slide, please. So here's an example. I'm going to walk you through the kinds of problems that which we had to understand what are the kinds of attacks that these various tools and proofs are trying to prevent. Okay. So this is the classic one, Crypto 101. All of us have seen this. This is Diffie-Hellman key exchange. Alice sends G to the X, Bob sends G to the Y. They compute G to the XY, and that's going to be the key. And we all know that this is vulnerable to a man-in-the-middle attack. Next slide, please. Where a man-in-the-middle is going to be tampering with the key exchange in a way that at the end of it, Alice and Bob think they're talking to each other, but they're actually both talking to the man-in-the-middle. Okay, and this is a well-known attack, and there's a well-known solution. Next slide, please. For example, there's the Sigma protocol, almost 20 years ago now, which is known to prevent those kinds of man-in-the-middle attacks because it uses a combination of signature and max, and that's why Sigma. And it has a nice cryptographic proof. It's provably secure. And if you go look inside the proof of Sigma, next slide, please. What you'll find is at the heart of it is this construction, right? The Diffie-Hellman construction. And there you have to make an assumption about the strength of that construction. And there are many different ways in which you can make assumptions there, but typically the standard hardness assumption you make there is that if I don't know X, or if I don't know Y, it's going to be hard for me to compute G to the XY. Okay? And this assumption crucially depends on how well this group has been generated, how strong that P, that prime is, modulo which we're doing all this computation. I'm not going to talk about this as if this is modular Diffie-Hellman in some sense, but similar arguments hold for elliptic curves as well. Okay, next slide, please. So what if the primes were small, right? So if the prime was really small, then we know that you can do a discrete log on G to the Y or G to the X, and you can extract X and Y and completely break the protocol. So obviously, the crypto proof that we did for Sigma only holds if that assumption is true for the particular prime and group that we chose. And if you go and look at the records for how small this prime can be, well, right now, we have been able to break all the way, people have been able to break all the way in academic settings up to 768 bits. We don't know if nation-state scale people can do better. But basically, we can break at least up, actually, we went one slide too forward, I guess. We can at least break up to 768 bits. So if you want a proof for Sigma to hold, you must instantiate it with the group, which cryptographers will say should at least have 2,000 bits, maybe even 3,000 bits in the finite field Diffie-Hellman setting. Otherwise, the proof doesn't hold. Okay, so that's how you interpret the crypto proof. The crypto proof is allowing you to uncover the necessary cryptographic assumptions on the primitives under which the proof holds. And now it's your job to go and then instantiate it in a way that the proof is not broken. Okay, next slide, please. But protocols don't just sort of support one group, right? I mean, all interoperable internet protocols are going to support at least like multiple groups, and some of them may be strong and some of them may be weak. So here's an example. Maybe Alice supports a strong 2,000-bit group and a weak 500-bit group, and so does Bob. So Alice is going to say to Bob, listen, I support these two groups. Bob is going to say, oh, let's do 2,000-bit Diffie-Hellman because that's good. That's the strongest group we have in common. And then we are going to continue with the protocol. And if all goes well, they're never going to use the 512-bit group. So you might ask, well, why do they support that 512-bit group in the first place? Well, the usual answer is backwards compatibility, right? So if you want to, if Alice is connecting to like an old printer or something, which has never been updated, it still is supporting some 500-bit group, maybe for that particular connection, she's willing to accept that weak group. But when she's connecting to Google, which has a 2,000-bit group, I certainly want to use 2,000 bits, right? And if all goes well, every connection like this between the clients and servers that we do care about is going to use a strong Diffie-Hellman group. Hence, it is going to satisfy the assumption that we used in our crypto proof. So the crypto theorem still holds. Okay, so if all goes well, that holds. But if you go to the next slide, but there's a protocol flaw in the protocol I put on the previous slide. There is a downgrade attack. And the downgrade attack is a kind of a man-in-the-middle attack again. Again, back to the same pattern over and over again for Diffie-Hellman. So there's a person in the middle. What that person is going to do is the attacker is that when Alice says, I support these two groups, the strong group and the weak group, the attacker is just going to delete the strong group from that message and just let the weak group through. So Bob is going to think that Alice only supports a weak group. So it's like some old Windows XP machine or something. And it's going to say, OK, let's do the weak group. So it's going to send back the 512-bit group. Now Alice gets this weak group back from Bob and says, well, maybe Bob is an old printer or something, so maybe I will accept this. So both of them have been fooled into thinking the other one is a legacy device with whom they need to kind of downgrade to 512-bit groups. And now the whole protocol goes through. We are using 512 bits, and obviously the theorem doesn't hold, the assumption is broken, and everything goes bad. Now, the thing to remember here is that even if you try to protect this, this negotiation like TLS does, using a Mac or something, it might well be the case, and this is what happened in TLS, that the mechanism being used to protect the downgrade, the protocol from downgrade itself was downgradable. So you could use the downgrade attack to completely break even the downgrade protection. So that's the attack called logjam, which came into 2015. It is a combination of this crypto flaw, which is that there are some weak modes, 512-bit sort of Diffie-Hellman modes, and a protocol flaw that allows us to go from a strong mode to a weak mode. So compose them together, we get an attack. Next slide, please. Of course, you could just say, let's eliminate all bad Diffie-Hellman groups from all implementations of TLS, and that'll be a very nice thing to do. So we have only strong groups everywhere, we're in this nice world. Then you still have one more thing to worry about, which are implementation bugs. Right? So what if you kind of disabled in your configuration in OpenSSL all weak Diffie-Hellman groups? Or maybe there's a bug in the code which will allow the attacker to trigger the code path that leads to weak Diffie-Hellman groups, even though you have officially disabled them. Right? So this is the kind of bug that led to a bunch of these attacks like Freak, Logjam, and Drown. There could be other bugs in the implementation of Diffie-Hellman itself, in the crypto library, so to speak. Your Diffie-Hellman computation might be functionally incorrect. It may have memory safety bugs. It may have side channels, right? And that can completely bypass the security that you intend for your protocol. So obviously, verifying the implementation is going to be important. So we've got crypto weaknesses, protocol flaws, implementation bugs, and they're coming together to break our security. Next slide, please. So how can we identify and prevent these attacks? Well, we are advocating the use of formal verification tools for this and formal analysis techniques, whether they're done manually or automatically. So there are three kinds of works that we are seeing in this domain, which are things that you can use. Well, the first kind of thing you can do is you can identify the core protocol that you're interested in and actually prove its cryptographic security. What that means is that you'll have to uncover all the crypto assumptions that you rely on and then show using a reduction or a game hopping proof that your protocol is secure if all these assumptions are met. To do this kind of proof, typically you need to include some kind of cryptographer in your team. It takes a significant amount of time. Usually the proofs are done by hand and they're quite involved because they involve probabilistic polynomial time Turing machines and so on. And it can take a few months, but it's worth it because at the end of it, you have a strong security theorem. To make your work a little bit easier now, there are some tools which I would encourage you to look at if you're interested in this zone, like EasyCrypt and CryptoVerif, which can automate some of the more sort of simpler parts of these proofs. You'll still have to do some thinking for the harder parts, of course. A second technique, and this is one I will advocate for almost everyone in the room, is that before you even start doing your crypto proof, maybe you should analyze the protocol symbolically to find all kinds of protocol logical flaws that you might have in your protocol. And for this, there's a whole bunch of really good tools available now. They're fully automated. You can specify your full model pretty compactly. I'll show you an example. And you can run these tools, and they'll show you attacks. Okay? And if you have kind of run it enough times and not found any symbolic attacks, you've at least given the protocol a good shake. And now you're ready for doing the actual crypto proof. Of course, after having done all that, I would encourage you also to kind of, if you have a prototype implementation or whatever, or a reference implementation, to verify that it doesn't have any bugs so that you have at least one clear way of showing that your protocol can be implemented in a secure way. And for that as well, there are a bunch of tools available that you can use. Next slide, please. And so the one we'll focus on is the one in the middle. Next slide, please. So all of this effort, like I said, can take months or weeks to do these kinds of proofs, which is not much if you think about the gains that you get from them, can all be made much simpler if the protocol itself were designed from the very beginning to be verifiable. And what do I mean by this? Because if you're writing a new protocol spec, what can you do to make this kind of formal method more accessible, more applicable to your protocol? Well, I would give you at least 5 recipes and 5 things that you can do, and there are many more, of course, but these are 5 I think are quite important. The first thing, which is kind of obvious, is that your protocol spec standard should precisely define your threat model and security goals. Now, This is like, obviously, doesn't every RFC do this? No, not precisely enough, actually, because we spend a lot of time, researchers, actually just writing those things down. So that's like almost a majority of our time. So finding a way by which we can communicate this between spec authors and researchers would be very good, because this is not precise enough right now. The second thing you can do is to use standard, well-understood construction, so we don't have to invent new security definitions for the way you use some combination of encryption and macking in your protocol, when you could just have used, say, AED, right? So if you use some well-understood constructions, we can use well-understood proof patterns. The third thing is if you break your protocol into kind of composable subprotocols, and composable is actually a keyword here, because it actually means something very technical, which is that if you can prove things about the subprotocols, the proofs and the definitions meld together well in order to give us a proof of the main protocol. This was the problem with earlier versions of TLS, which was solved at TLS 1.3, and this is actually kind of very important for a lot of the proof techniques to work well. A fourth thing is that if you have two different versions or two different modes of the protocol, you have to it's best to actually completely avoid any key reuse between the different modes. But if you can't avoid all key reuse, then very strictly limiting how a key that is used in one mode can also be used in a different mode is critical. Otherwise, you have to verify all of these things together. If you can limit this, you can verify the different modes separately, and then they don't interfere with each other. And the last thing is, well, you want to help programmers, of course, write implementations that are easy to prove correct, and therefore easy to be correct. And to do that, there might be some standard data structures and state machines that you're using in the protocol. It's best to specify it, because without that, people are just inventing their own ways of doing this, and they're getting it wrong. Next slide, please. So the TLS 1.3 experiment, what it did right, I would say, is that it actually did a lot of these. This was a big part of the effort, was to actually implement many of these patterns to actually make the proofs even feasible. So all the papers at the bottom were only possible because the design team agreed to make many changes in design and redesigns in order to make the cryptographic analysis easier. In some cases, well, there was just nothing to be done. For example, 0 RTT. So despite many complaints, it remains in the standard. But in many other cases, actually, the protocol changed a lot, even sometimes at the cost of performance. So I'm going to show you a little bit more about one particular analysis technique, which is the one which I've highlighted there, which is a symbolic protocol analysis technique, which I think can be more useful and has been already applied to many other protocols, not just to TLS. Next slide, please. So let's set a target. So let's assume that we've got tons and tons of proofs of TLS 1.3, right? So let's assume that all the modes of TLS 1.3 are provably secure. They're as solid as can be. We don't have to worry about them. But we do know, because of all the red stuff before, that there are some modes of TLS 1.2 which are broken. There's some obscure modes maybe, but there's some modes which are broken. So, and we also know that for the foreseeable future, TLS 1.3 is going to be deployed and run on servers alongside, side by side with TLS 1.2, just for backwards compatibility. For maybe 5 to 10 years, this is going to be the case. So how can we be sure, despite all our proofs of TLS 1.3, that an attacker will not just do the same man-in-the-middle attack that we talked about? When somebody is trying to connect with TLS 1.3, just downgrade it to TLS 1.2. Now we are in TLS 1.2. We know there are some broken modes. Exploit the broken modes, and therefore just jump down the ladder until we can get to an attack, and then break the protocol. So is there a downgrade attack on TLS 1.3 that will completely void all the proofs that we did for it? Hopefully not, because we actually tried to put in downgrade protection countermeasures in TLS 1.3, but how do we verify that they work? Next slide, please. So one technique is, well, let's analyze it. Let's formally analyze this protocol to make sure that it cannot be downgraded. How do you do that? Well, the first thing you have to do to do a symbolic protocol analysis is you have to write down a model of the protocol in some formal language. So, for example, you can write it down in a language called proverif. And the protocol on the right, which you can't really read, is the whole TLS 1.3 1RTT protocol and its key schedule. Well, it kind of vaguely fits on a page. It's not super duper complicated. There's also, of course, a 0 RTT mode. And in this case, we also want to check for downgrades to TLS 1.2. So we'll also have to model TLS 1.2, which is equally complicated. But however complex these protocols are, when you actually write down the cryptographic model or the protocol model for these protocols, 1.3, 1.2, 0 RTT, 1 RTT, everything put together is about 500 lines of proverif. And it can be even more compact if you like. Okay, so it's like a few hundred lines. You can just model the whole protocol. That's not the hard bit. And I'll show you in the next slide what the model looks like. The hard bit is how do you specify what your threat model is and what your security goals are, and how do you understand what the results of the analysis are actually telling you. So how do you map what your desired goals from TLS are down to this tool and kind of map what it's saying to what you actually want to prove. Next slide, please. Well, this is, again, probably unreadable, but this is what it looks, the protocol model itself looks like in ProVerif. All I wanted to show you was that, well, if you're used to programming in something like, I don't know, Haskell or OCaml or Python or whatever, any of these high-level languages, it won't look very different. You just basically are coding the sequence of cryptographic operations that is happening in the protocol. It's just code, really, okay? So that's just in its own syntax. It has its own formal semantics. There are some threads and some messaging, but okay, it's not going to be rocket science to write down that model, okay? What's interesting, like I said again, is how do you model the threats? So next slide, please. So in a tool like ProVerif and Tamarin, what you're doing is symbolic protocol analysis, which means that you have a symbolic threat model. What that means is this model, which was originally designed by Needham and Schroeder and then elaborated by Dolev and Yao, which is basically of a network adversary. So then the attacker is someone who can read, write, tamper with any message on the public network. The attacker can also play the role of a client and play the role of a server on any session. The attacker can also compromise certain servers and certain clients by kind of stealing their long-term keys. And when all of this is said and done, we ask, well, can an attacker now break into a session where it has actually not it's not playing the client or the server? Both the client and the server are honest. Are those sessions safe or not? The one limitation we put on the attacker in this model is that, when you think about strong crypto algorithms, we treat them as completely perfect. So the attacker cannot break into strong crypto, cannot guess long keys. It's not like a probabilistic argument. We just say possibilistically, the attacker cannot do it. It's a black box. And that kind of simplifies the analysis a lot. So in order to deal with downgrade attacks, we also have to extend this classic model a little bit. So we have to extend it with the idea that some algorithms might be weak because otherwise there's no point in doing downgrades, right? So what we do is we can say that every primitive has two versions, a strong version and a weak version. If you use the strong version, it's perfect. The attackers cannot really break into it at all. If you use the weak version, you're completely host. I mean, the weak version of that crypto primitive gives you no guarantees whatsoever, okay? And now we want to ask the question, can an attacker who can break weak ciphers and who can do all those network attacks that we talked about and be a man in the middle into any protocol session, can such an attacker break the security goals of TLS? Next slide, please. And what are these security goals? You have to write them down, right? So in ProVerif, you'll have to write down, well, what is your secrecy goal? What is your authenticity goal? Do you want to prevent replays? Do you want forward secrecy? And each of these goals you can write down. Some of them will be true, some of them will be false, right? So replay protection does not hold for 0 RTT data, but it holds for 1 RTT data. So these are all goals you can write, and you can evaluate the protocol and say which messages enjoy these properties and which messages don't enjoy these properties. So the simplest of these goals, and that's what we're going to look at, is the secrecy of messages. So let's say you want to ask, is the first message sent by my browser to a TLS 1.3 server, S, is that first message kept secret? If the server is honest, if my browser is honest, is that kept secret? So you can write down that query like the query at the bottom of that slide, and you can ask ProVerif, please prove to me that this is secret. Next slide, please. And ProVerif will say no, and it'll give you a trace and a counterexample and say, no, there is a sequence of actions in the protocol model, which is this 500-line model we wrote, which at the end of which the attacker has this message. And that, if you look at what's actually happening there, you'll find that in that particular trace, the attacker has compromised the server's private key and is able to, therefore, break the secrecy of the message. Is able to impersonate the server, get the message that this client is thinking it's sending to the server, but the attacker gets it. So you say, oh, okay, we only want to consider sessions where the server has not been compromised. So you can ask a second query. Next slide, please. And now you say, prove that the message is secret as long as the server is not compromised. ProVerif will run this again, own your whole model, find an entire trace of messages, and they'll say, yes, I found a trace where, in fact, the attacker can get the message even though he has not compromised the server, because that particular trace uses a weak AEAD algorithm or weak encryption algorithm like MAC encoding crypto or something. Next slide, please. So you can say, okay, no, I know that in TLS 1.3, all my AE algorithms are strong, so I want to remove that case as well, and say, okay, is there any other situation in which this happens? And so on. So you can keep iterating with your goals, and Proverif will still keep searching through all possible man-in-the-middle attacks and try to find you ways in which that goal could fail. And if you keep going on, next slide, finally you get to this is the strongest goal that we can prove for TLS 1.3 secrecy. It says, it lists all the particular cases in which the message from the client to the server could be known to the attacker. And at this point, Proverif says, no, I cannot find any symbolic, which means a network-based attack that will break this. Okay, next slide, please. So how do we interpret that query? Well, if you read through what it actually means, what it says is that all messages on TLS 1.3 connections between an honest client and an honest server are secret, as long as the following 4 conditions hold true. Okay, the server is honest, the client is honest, plus 4 conditions. That this particular connection should not use a weak AE algorithm, which is okay. TLS 1.3 shouldn't have any weak AE algorithms. This connection should not use a weak Diffie-Hellman group, which is again okay. TLS 1.3 should not use any Diffie-Hellman groups, weak Diffie-Hellman groups. The third one is that the server promises it never uses a weak hash function when signing with the same key that it's using on this connection on any other session. So even on some other session, if it uses a weak hash function to sign with the same certificate key, that other session could be used to break the session I care about. Okay, so this is actually a global property. That server should not use a weak hash function with any other protocol if it's using that key. Similarly, the server should never participate in TLS 1.2 RSA key exchange, because if it does, then there is a cross-protocol attack between TLS 1.2 RSA and TLS 1.3 RSA signatures and TLS 1.2 RSA encryption, and at least in our model, that attack is considered to be valid. So this essentially, if you look at these, it gives you the minimal set of conditions or preconditions under which TLS 1.3 satisfies that secrecy goal that we set, and therefore is downgrade resilient in some sense, as long as those conditions hold true. Another way of looking at it, it is giving us a limit on all the weak algorithms that we have to watch out for in TLS 1.2, because they might break TLS 1.3. They might be breaking TLS 1.2 too, but maybe we don't want it to break TLS 1.3. So I have focused most of what I've been saying here on TLS because, we are giving out TLS t-shirts at the back. It's kind of a success story and so on. But of course, a lot of the techniques I'm talking about, they don't just apply to TLS. They apply to any security protocol that you care about, right? So I'll talk a little bit more about OAuth 2.0 because that's actually an interesting case. But indeed, verification tools like what I've talked about and methods have been applied to OAuth 2.0, which is nothing like TLS, right? It has also been applied to ACME to find attacks and do proofs. It has also been used recently to find attacks on this 5G AKA protocol by Kramer et al. And these are exactly the kinds of analyses with the queries and symbolic proofs, man-in-the-middle attacks that I'm talking about. Well, later today, there's an MLS BOF, and in fact, MLS already has a model for some parts of the protocol, and we are working on models for more and more of it. And we are hoping that this will also be a case like TLS, where we can apply a lot of these techniques. So let's look a little bit at OAuth, which is a very different protocol from TLS, just to see how it looks like. So OAuth is what we are using, and most of you probably know this, right? What you're using when we go to, say, Pinterest and say, I want to log in with Facebook. So Pinterest is going to forward me via an HTTP redirect to Facebook. I'm going to log into Facebook. Facebook is going to generate an access token. It's going to redirect me back via an HTTP redirect back to Pinterest, which now gets the access token from the URL, and I'm logged in. Yeah, it's a double redirection protocol. It uses HTTPS underneath, but in the protocol itself, there's hardly any crypto. I mean, there's no crypto actually. Inside the access token, there could be some crypto. There's in OpenID Connect, which is on top of OAuth. There's an ID token which has a little signature inside it, which is kind of important. But really, it's very lightweight on crypto. So if you just look at that protocol, it's just like whatever secure channels, 2 messages or 4 messages back and forth. It's very simple. People have analyzed this for many years now. We think we should understand this protocol reasonably well, right? But to analyze this protocol, there's a big hole. The hole is the following. The protocol is running in the browser, right? And the browser is a different beast to TLS clients and servers. So I might be connecting to Pinterest on one tab and doing this OAuth protocol. On another tab, I might be connected to, I don't know, dancingbunny.com. And dancingbunny.com might try to interfere with my OAuth flow. So this is a web attacker, an attacker who's able to run JavaScript and run on other tabs on the same machine where I'm running my wallet protocol. And this requires a completely different kind of analysis. It's a way more powerful attacker in a certain way than the $Yao symbolic attacker I showed you. And even modeling this attacker requires you to give some meaning to the term same origin policy, which, as many of you might know, is kind of a very fuzzy term at the best of times. So just to give you an idea, if you look at the OAuth RFC, of course, it's 76 pages, the security considerations, which lists a long list of web attacks, of which could be possible and how they can be ameliorated and how some of them are ameliorated by the spec, is another 70 pages. So this is like the threat model is almost as large, or I would say much larger in a certain way than the protocol. So a bunch of researchers in Stuttgart did a formal analysis, a proper security analysis of OAuth 2.0. And the large part of their model is actually just modeling web security, web threats, cross-origin, same origin stuff, so that they can even state what OAuth security goals are. The paper is 95 pages long, okay, and the model is really, really huge. And they did most of their proofs by hand, but they're trying to automate it now. But it's just an example of where the protocol itself looks trivially simple, but its threat model and security goals can actually take a lot of effort to formalize and prove things about. And that is actually important, because in doing that proof, these guys found attacks, many attacks. One classic one, which some of you may have heard of, is the IDP mix-up attack. If you squint and look, it's a man-in-the-middle attack between a client and two servers in this case. It's a classic symbolic attack in the network protocol sense, but it only appears if you model exactly what the features of the web that are being used here are. There are other attacks which rely on actual details of what code you're using for the HTTP redirect and so on. And these are kinds of attacks won't appear if you don't understand what exactly the underlying web security model is. So this one has got a countermeasure in the OAuth, and RFC for the countermeasure is probably going to be standardized, but this was one of the attacks that they found. All right, next slide, please. All right, so I'm almost done. What I wanted to impart to you is that there are these bunch of tools and bunch of methodologies that we use for TLS, that we are hoping to use for MLS, that people can use for a variety of protocols. And these kinds of analyses can find bugs and flaws and in your protocol and in your crypto, in the underlying crypto of it. And if you do the proof, it can provide you some pretty strong cryptographic security guarantees. Using these kinds of techniques, doing these kinds of proofs certainly requires some expertise, okay? So it requires, well, a PhD student in my case, but maybe for you it requires something else, right? But the tools are improving. We are hoping, and unless we do more case studies and collaboration with people who are designing protocols, these tools won't improve. So we really need to exercise it together in order to kind of get this field into a better place. And the TLS 1.3 experiment, I think, shows for us, at least from the researcher point of view, that if you design the protocol to ease analysis, that actually makes things much easier, and kind of, I think it's a good trade-off in many cases. But before we even start using any tools, the first thing that we all have to do anyway, whether we are the verification guys or protocol guys, is to write a spec, right? And if you can write a formal spec, that really eases the way into doing any of these proofs. So I'm going to encourage all of you to start kind of at least write one formal spec for your latest favorite shiny new protocol. And this spec you can write in any of the languages and whatever format you like. There's a whole bunch of them that are coming out. If you want to write a new crypto primitive, there's something called HackSpec that we're working on. If you want a protocol, there's Proverif, there is Tamarin. If you're interested in doing a crypto proof, write it in EasyCrypt, for example. And there's a sort of principle in the verification community that if you just write down formally your protocol, even before you start doing the proof, you're probably going to find bugs. And people have always found this to be the case. So just writing down things precisely, the threat model, the security goals, and the protocol model already sort of exposes tons of things that you may not have thought about, even though you've been thinking about the protocol very hard for a long time. So I think I'm done. There's I think these slides are online, so I just gave you some pointers where you can go find these tools. Thank you for your patience. And questions are welcome.
Hannes?
Hi, this is Hannes. I'm a co-chair of the OAuth working group, and thanks for the presentation and for mentioning the paper that led us to start a series of OAuth security workshops where we try to engage with researchers to get their expertise on formal verification and also crypto stuff. One observation we made was that researchers are motivated to start fairly late in the process, ideally when the stuff already is widely deployed, so that any vulnerability they find has a significant impact, which is kind of understandable from their incentives. Of course, it's not very helpful for us, though. So luckily, it worked out differently in TLS 1.3 and now more recently with our continuous engagement with the OWASP community. But in general, I think the only approach that works is to get IETF participants to actually do the formal verification themselves. This does, however, raise another challenge, as you mentioned, that most of the formal analysis takes actually more time than the protocol work itself. And it's difficult to say whether people are really prepared to do that. And the tools that we have are also a little bit, so there are a number of different tools. You mentioned some of them, but there are many more. And all of them have used a slightly different syntax, different properties. They have certain limitations. The support is different. And if different groups work on different tools, then the reuse is very difficult. In general, like composing different protocols, as we often do, and it doesn't translate nicely to these tools. So you can't easily say, I'm using TLS, so dump in a specific TLS configuration, I'm adding just OWASP on top of it. That doesn't work that way. So there's the challenge of, I want to have my tiny little extension to TLS or some other protocol, and then I essentially have to go through this week or even months-long exercise of doing the formal verification because everyone else was doing something else. So I think we have to potentially look at what is specifically needed for the IETF protocol community, and which tools are available and which ones are actually still supported, because then you can easily run into a lot of frustration there. But in general, I had noticed myself that most of the IETF protocols are not really at the level that you could immediately produce a formal model out of it, because it's lacking a description of the security goals, because the interoperability need is often very different from what you need for the protocol analysis.
That's right. Thank you. I don't think there was a question there, but I will just make a comment, which is that indeed so this has been a problem, the fact that there are so many different tools with so many different languages. The way the languages are designed for these tools are so that it's easy to do certain kinds of proofs automatically. So they're geared towards proof rather than trying to make it most usable by most number of people. And that's kind of unfortunate. We identified this, at least in the context of crypto primitives. So I gave a presentation at the CFRG on hack spec, where we are trying to design one language where you can write your crypto primitives that will compile down to all the various tools that all the people who are doing crypto primitive verification can go. Maybe one day for protocols, we might have and we'll probably try to write an informational RFC on that language, which can be used by the IETF. But hopefully for protocols as well, we can come up with something.
Hi, Ted Lemon. So you had a slide kind of way back towards the beginning that had like a list of 5 things that I really love this slide. That's the one, yeah. Is there any resource that would be available to somebody relatively naive like me so that I could learn about these things? Or is that just sort of like do I have to go get a PhD first?
Well, well, there are different levels actually, right? So the last one is fairly protocol specific, but but indeed for well, let's see. Let's assume that you wanted to do crypto proofs for some protocol which you're going to be developing. You haven't fully developed it yet, and let's say you just picked a tool which is EasyCrypt. EasyCrypt will have a library where it will give you, these are the 20 definitions which are being defined, which we understand, which the tool does very well. It'll be UFCMA for signatures, INCTXT, whatever. There are these 10 constructions that it already has. So you won't have to add anything new. So as long as you pick from the standard constructions there, the tool is going to do very well for you. Okay. Plus, you're less at risk of screwing up in actually modeling this stuff, right? So that's the kind of way I would go for this, right? So, and when I'm talking about sub-protocols, usually you mean like separate the key exchange from the record layer and these kinds of things, which are well understood principles. And maybe we should write a document that clearly puts this out. And,
yeah, that's kind of what I was getting at, because just what you just said helped me, but it still wasn't. I still feel like, oh boy, I've got a whole bunch of learning curve to climb here, and I think it's worth climbing because we keep getting bitten by these things. So I'm just thinking that if there were a document that kind of was like a toolkit for somebody like me who's not really an expert or even remotely an expert on this stuff, could use to get close, and then maybe at least know the right questions to ask of somebody who is an expert.
That's good feedback. Thanks.
Yeah, thanks.
Hello, Phil. I'm Phil Hallenbaker. As it happens, I do sort of have a doctorate in this, because this was allegedly the subject of my thesis 30 years ago. I am very keen on formal methods as a pedagogical exercise, because the thing that it teaches you more than anything else is the value of simplifying your design. Because if you don't, it is always easier to simplify your design than construct a proof for a complicated one. I am a little bit cautious in that one of the effects that I've seen is people going for things that we can prove are correct over things that are robust in the face of a poor implementation. And those things are not always the same. That said, one of the things that this might help us get over is we tend to see a lot of, we use TLS a lot as a hammer that we know because it's the one that we use and we're comfortable with. And it's often not the right hammer to use because it's big, it's complicated, it has a lot of moving parts, and it can go wrong. So it's not always the thing that we should be going for, but it's the thing that we tend to end up using. So if we go to formal methods more, we may be able to get out of always using the same tool, even when it's not the most appropriate one. So one of the things I'd like to suggest is that we have a mailing list for folk who are embarking on this brave new journey into the tools, because obviously you didn't have the tools when I was doing it. And, maybe we could teach each other what the heck's going on and maybe settle on we're not going to be using all 5 in the IETF.
No.
Yeah, I think that we're going to narrow down, and if people's proofs are going to be any use, it's going to have to be proofs that we can all share. So I think it would be a good thing to have a mailing list.
Yeah, making mailing lists is pretty easy. Just send us an email. We'll get work on it.
Kartik, I have a question for you. This one is, I was wondering whether you think it's worthwhile to entertain a discussion about the different tools, the formal method tools, and which ones are most suitable for the IETF protocol context. And maybe there are some that shine here. I know, of course, you have some preferences because you worked on some of them yourself or defined them yourself, but maybe they are all not quite there in terms of what we need for the IETF community. There are obviously trade-offs here. So,
so my experience with protocols and my comments can only be based on the few protocols I've looked at, and I know that the IETF is standardizing so many different variety of things that it'll be useful to understand what the scope is. The reason we have what I would say 2 leading tools or 3 leading tools in each of these zones is because they do some things well, better than the other one, and both ways. So there isn't like a clear winner that I can pick out. Even if you said to me that the IETF context is a particular one, I don't think there'll be a clear winner. But maybe we could find some way of at least kind of settling on something that will work in most cases.
But just to be specific, for example, if I compare Skyfire with F-star, there we are talking about a completely different type of complexity and level of understanding that anyone here needs to have in order to write something. So, and it also depends whether we just want to do a formal analysis or want to also have other sort of backends to do, let's say, test case generation. We may even generate code. Some of the tools generate code, as you pointed out. So there are different goals, and I'm not sure which ones of those tools are obvious, which would the learning curve that has been talking about is significantly impacted by the choice of tool you use.
Yeah.
Because
I agree. I mean, so in response to an earlier question, it'll be nice to figure out a way in which we can get, I think you should be able to get the easy stuff done easily without too much learning. And now that you're going to hit a level of complexity where you have some composition of a post-quantum something with something else, and then you might have to actually put in that extra learning curve. But indeed, we should make the easy stuff easy. I think. And I think that's a good challenge for the research community. And we can be motivated by the fact that there will be people consuming our stuff. So, and in answer to an earlier question you had as well about the motivations of the research community, we like to publish papers. And indeed, for that, we have to show impact sometimes. And maybe if, maybe we can have some policy by which the IETF working group chairs can give us a little letter saying this has had great impact or whatever, and then you won't have to wait for the end of the RFC and break the existing implementations, right? So to get that impact from that.
I mean, maybe a two-stage approach where you start with something simple in the working group and then have the more complicated version done by researchers, which
maybe
just
Tobias, you said you have a 97 pages paper for a formal model of a browser.
Yeah, it's not me, but it's,
how long would that be for an operating system? And you would need one, right? Or even for a platform, like if you're talking about IoT and stuff where you actually have physical threads.
So let's be clear, this is a very limited model. Yeah? This is just doing the browser security mechanism. So it's just cookies and CORS and redirects and HTTP fetch and this kind of stuff. It's just the things that kind of get exercised by OAuth, really, that zone of things. Indeed, I mean, there is a project called SEL4 out of Australia, and if you look at their work, it's taken them years and years to build a spec for the operating system. It's a very small operating system, but even so. So this stuff can get very large. You have to, I think, pragmatically choose the component that you care about. And I don't recommend doing whole system verification. I don't believe in it because it's kind of a bit Nazi-ism. I mean, that you should pick the component that you care about and try to make sure that one is robust. And the cleaner and the more you can separate it from the rest of the system, the more confidence you can have in that your proof actually means something.
Let's thank the speaker.
Yeah. All right. So we got Harry next.
Yep. Next we have Harry Halpin to talk about the syncs packet format.
I just tell you what the slot changes.
Yeah. Although unless Ben wants to try to do the driver install now.
I'm happy to fix something. It's okay. Okay, so now for something completely different, although somewhat related, which is a packet format. How many people here have heard of the Sphinx packet format? Just wondering. Very few. So it's a, next slide. So I apologize for not being designer of the packet. Unfortunately, he cannot escape his teaching duties. It's a provably secure and compact, secure mixed networking format from George Denisis and Ian Goldberg. So to relate to Karthik's talk, it has security proofs. And the goal is how do we send a packet from one hop point in a network to another one, and making these packets completely unlinkable. That means completely privacy preserving from both a sort of large scale passive global adversary, and an active adversary, which perhaps is corrupting the network nodes, which are sending the packet around. And it has a bunch of interesting properties. It's about 10 years old. It's withstood the test of time. Alternative designs have, in general, had some sort of breakage. Keep going. Next. So the intuition is that first thing is all of the packets have to be the same size. This isn't really a security intuition, it's sort of a privacy intuition, so that each packet is indistinguishable from each other. And you don't want, you have to, this is a sort of CFRG note, but we need a wide block cipher for this. Wide block ciphers, AEZ is the original one, now we have Lioness, now Farfalla, but they're sort of, otherwise the enemy could sort of corrupt it and link the two packets en route. The core cryptographic intuition behind Sphinx is that it's sort of an extended Diffie-Hellman. You have a network, people have keys, you're a client, you want to send a packet to another node of the network. If you could do a sort of Diffie-Hellman with that other node, then you can take that Diffie-Hellman and break it up into lots of little Diffie-Hellmans, and then use those little Diffie-Hellmans to sort of pass pass the node in an encrypted way between a different bunch of different routers. So this is very similar to onion routing to some extent, but it has a few differences. So one difference is that the goal of the Sphinx packet format is to keep the routing network information, the header, the Sphinx header, essentially constant size and encrypted such that for each hop, you basically decrypt the header, not the whole packet, and you can look at after checking a MAC, make sure it's not been corrupted en route, look at sort of the information for the next hop, and that no one knows all of the hops except the client. And that's, I think, quite a useful trick. And we'll go for the next slide. And this is just a sort of large-scale version of how it works. Essentially, the alphas are group elements. The betas are the rest of the packet, the sort of routing information, which is encrypted. And the gamma is the MAC and has a payload, as you can see, which is really separate from the header. And just at each hop in the network, you essentially, you use the shared secret you've established using whatever PKI method you want, which people have very different preferences on this one, and you just decrypt it. You basically deblind. You get the next group element, which is allows you to do the next hop. You pad, move the rest of the routing network forward. You have to pad because remember, you want to keep it constant. Otherwise, the length of the routing information could allow attacks, linking attacks. You would know how many hops are still going or in the future going forward. And it prevents you from doing things like mixing the packets together. And of course, you need the MAC to check the integrity at every step. And you just recalculate the integrity of the routing information before encrypting it and put that in the routing information and then encrypt it. And that happens every hop. That's like the core intuition. Next slide. And you can see, that's the details. But if you want the details, I highly recommend you can just look at the paper, or we have a draft spec. But now for why would you want a standard for this? This seems a bit academic. Next slide. Well, there's a lot of use cases. And even though the original work has happened quite a while ago, there's been increased sort of interest in anonymous communication technologies. Some of this is actually coming from the blockchain world. The Lightning Network, which is how you do direct peer-to-peer communication in Bitcoin, which is being deployed, has been deployed in May 2018 with a beta test network, but really is going to be deployed by Blockstream and the rest of Bitcoin Core over the next year, uses Sphinx as its direct sort of format to send payments between Bitcoin nodes. Stellar and a lot of other companies which process sort of tokens or coins of various kinds are all building Sphinx-derived packet formats for their payment transfers. Messaging systems. So we have a lot of there's a lot of interest in next generation encrypted and privacy enhanced messaging. You see the MLS work booting up here at the IETF. But, encrypted messaging is only one half the battle. How can you make sure you don't know who's communicating to who? And this is where the Sphinx network format is absolutely necessary. Strangely enough, the same general intuition is used in voting systems. So the state of Greece is already deploying Sphinx in their e-voting systems through the work of GRNet. And Estonia, who has sort of probably the most advanced e-voting work, is also looking at this format, although they don't currently use it. And you're seeing some adoption in terms of the General Data Protection Regulation. So, for example, SAP has started working on with MixNets and Sphinx on privacy-enhanced statistical analysis of data. So, what we're seeing, next slide, is we're seeing tons of incompatible libraries happening. So even though most of this work is pretty, I would say, early stages, despite the core cryptographic design being almost a decade old, while we maintain one single Python library with a test suite, Java and JavaScript compatible libraries as well, we're seeing a plethora of incompatible versions in Go, C, Python, and the Lightning Network is also incompatible, and they're producing even different extensions with different incompatibilities. And due to these incompatibilities don't change the core cryptographic design, but they change very basic things. So if your routing information, for example, is dynamic, you're going into a network, and let's say you enter via, you need an authentication credential, you hop around using sort of normal TCP/IP, but then you want to exit let's say an email server, or you want to X into a different network, all this information basically is no longer maintains the critical assumption of Sphinx, which is that your routing information is fixed, but it may be dynamic. And so there's a lot of work on how to do that, and we haven't really settled. And this is not really a crypto problem. This is a network level engineering problem. And also there's been cryptographic requirements that have changed since the work was originally put out there. What we're seeing due to all the discussions around elliptic curves is, the original papers kind of, you can use RSA and elliptic curves, but now we're seeing, people use curve 25519, other people use different curves. The wide block cipher space is a bit of a mess. We don't have any CFRG recommendations on it. There are known attacks in AEZ. And efficiency, a lot of the latest changes we're seeing through the work on, for example, Adrian Perig's Skyon, which also uses Sphinx as its underlying packet format. It's pretty exciting work that we believe will be deployed, is that there's different assumptions about, how many times you should encrypt or decrypt, basically, different threat models. And these leads essentially different extensions to the core. And so we would hope, next slide, that we could eventually get a spec. And we believe this incompatibility is caused because we don't actually know many of these people, particularly all of the blockchain work going on. But what they do is they Google Sphinx, they read the paper, they code the paper up, everyone's coding it a little bit differently. And if there was an IETF, even informational draft, we could probably rather easily get everyone to Google the same thing, and they would then have access to the same test suite and the same spec. And that we think would be great. We have a draft spec. We'd love to get in touch. Mailing list informally on mitsnetworks.org. A lot of this stuff work is coming from an EU project, the Panoramics project I'm an advisor on. We're using a bunch of other work, and we're just interested to see if the IETF even believes that this sort of work, which is on some level old, but on another level cutting edge and deals with anonymous communication, is something even in scope for IETF, and if there's any interest from the IETF participants in pushing this work forward. So that's it. I think I kept that 10 minutes.
You did.
Okay, excellent.
Any questions for Harry? Comments? Okay, well, if you're interested, see you here afterwards. Yes, our next speaker is Nadim Kabisi, talking about his work on Capsule. So we surveyed lightning-ish talk. And I hope I pronounced your name right.
All right, so I don't have a lot of time for this, so I probably should start up.
You don't have to start until you get your slides. We'll
okay.
You on the clock.
All right, so this is a very quick talk on a Capsule, a protocol for secure collaborative document editing. Next slide, please. Haven't you all been there? You open Google Docs and you're typing up your plan to conquer the world, or your very secret work secrets on collaborative, no, wait, hold on collaborative editing, but you don't know where that document's going. You need to collaborate with your coworkers. However, it's being shared on Google servers. It's available in plain text or on Microsoft servers. Don't you wish there was a better solution? Next slide, please. Introducing Capsule, a better solution. Capsule is a end-to-end encrypted protocol for, well, it's a protocol for end-to-end encrypted collaborative document editing. It has security goals like participant list integrity, confidentiality, wow, integrity, amazing, authentication, whoa, transcript consistency, incredible. All in one protocol? Next slide, please. You see, in Capsule, we take the patented, and you've really been tired of it, but not in the way we do it, blockchain. And a document is essentially a hash chain of diffs. Access to a document is obtained by sharing a simple ID. Incredible. Users must prove knowledge of the ID to participate in the document. Wow, I used the word proof. I must know what I'm talking about. Primitives, Blake 2 for symmetric operations, and ED25519. DJB designed it, it's fashionable. Great. So I'm really in group, aren't I? So, all right, next slide. Yes, we have a protocol level is formally verified with ProVerif. Whoa, the guy with the most minutes talked about that. And also hand proofs. At the implementation level, we use F***. 5 people in the whole world know how to program in F***. That's how incredibly difficult and complex it is. But we use it. And so we have like formally verified primitives. We have formally verified the protocol. There's a hand proof for the protocol. And on the implementation level, we also, from the get-go, have an implementation with functional correctness and resistance against side channel attacks and so on. Next slide, please. So this is an open standard for end-to-end encrypted collaborative document editing. This is obviously a use case that, I mean, obviously this is clearly something we all want. The protocol, I managed to design it in a way that's pretty straightforward. It's really, I mean, I think a simple, elegant protocol. We can prove it secure very easily. There's an implementation that's readily available with nice primitives and clean code. This is an open standard. I think this should be an IETF thing. I think that's really a no-brainer. So let's talk about that. Everyone, I think, agrees that the use case is important, and it's an easy problem to solve. It's not like TLS, you have to worry about a bunch of stuff. It's actually pretty straightforward. So you can go on the website, symbolic.software/capsule. There's also the ePrint paper, which is also on the website, but you can just email me or talk to me, and then we can make an IETF RFC, and then everyone benefits, and we solve an obvious problem. So thank you.
Anyone have any questions or comments for you? No.
Right. Thank you.
Thanks.
Really helped liven things up.
So, Stuart and/or substitute Stuart? Ah. Also, we have this one more guy, Yankee Stuart. That's what.
You got the zapper, yeah.
Sorry, that doesn't work.
Oh, okay, all right, no problem. So I'm the sacrificial routing guy sent to the lion's mouth here. So can we have the next slide, please? So we've got a problem in routing. The control planes we use are often carried over very simple transport layers such as UDP or TCP. Control planes are good targets for attack, and their disruption or subversion can have serious operational consequences for our networks. There's a good example documented in RFC 2385, I believe. LDP, the label distribution protocol used in MPLS, and pretty well every packet you send across the internet goes across MPLS somewhere or other. That's a key protocol. LDP runs across TCP. It currently uses TCP MD5 for authentication, which is no longer considered secure. And this is frequently pointed out to us when we send one of our documents for publication, including documents that are just a minor extension of LDP itself. So next slide, please. We've done a small survey, not a particularly scientific one, but a sort of tiny survey just to see what the world looked like. So we asked some operators if TCP/AO, which is the obvious alternative way of securing a TCP protocol, if TCP/AO were available in products, would you use it? And are you planning to deploy it? And we asked some vendors whether they have TCP/AO available. And I think what we've concluded is that we need to ask the question more thoroughly. But the answers we got so far are illuminating. Next slide, please. So what we hear from the operators we did speak to is we've got no real plans to deploy TCP/AO as long as the vendors support their MD5 implementations. And some of them told us that actually, there are very few authenticated LDP sessions in use. I think they use a lot of, for peer-to-peer adjacent LDP, MACsec is quite commonly used anyway. But we also have targeted LDP, which goes over several hops. The concern is the cost of reconfiguring their network and rolling out TCP/AO. Now, the vendors
also answered, saying, well, naturally, most of us don't have TCP/AO in our products, although one did say it would be available later. And what they tell us is they will not implement it until they hear from the operators that it's needed. So this is kind of a just-in-time development strategy that the product managers run. Next slide, please. So what we think we need a security suite that is more secure than MD5. By the way, I should say this is for authenticating packets. We don't worry about the routing stuff being encrypted. We just want to make sure that no one is tampering with it. So we want something that's more secure than MD5 when used over the long-lived sessions that support routing. There was someone this morning in the MPLS session saying that they had a routing session that was up for a decade. So we're talking about short sort of web page type grab, get, and throw it away. We're talking about very, very long running sessions between routers. It needs to be able to run on most existing root processors. Now, root processors are not like the processors you have in server complexes. They're not the latest hotshot technology. They're often really quite a Cinderella child in terms of being begrudgingly given some CPU horsepower. That's the way the world has been. It needs to start up and run fast so that it doesn't impact reconvergence even from a cold start. That is to say, if I have a power down in the on the router and I bring it back up, it's got to come up sufficiently quickly that this is not the long pole in the tent in terms of reconverting my network over the optimum paths again. It needs to be sufficiently operationally complete and easy to use that network operators will deploy it. And it needs to be compelling to those operators so that they will demand it from the vendors who will in turn implement it in the product. Next slide, please. So what we're doing, we're looking at TCP/AO as the obvious solution, but we think we probably need to look a bit wider and see if there's anything else that's even more obvious given the needs that we have. We're coordinating with a number of the protocol groups that will use this, BGP, MSDP, and PSEP. We're talking to a number of the routing groups, IDR, PIM, PCE, BES, RTGWG, PALS, and MPLS. A lot of groups are in this same position. There was a discussion this morning in the MPLS working group, and we're here to ask for long-term guidance from the security area as we work on the problem. Next slide, please. So there's more detail in the draft, and attached to this slide deck is an excellent slide deck that Jeff has put together, which he gave to the IPEG meeting on Sunday to get their perspective on it. So there's more details in it, but I'm not going to discuss it today. Next slide, please. So why am I here? I need help, or we need help. The routing teams cannot do this on their own. We need long-term help from security designers because although we know about routing protocols, we are not security experts. A Rolls-Royce solution to this is unlikely to find its way into RFPs that set the implementation specifications. It's got to be a pragmatic, simple approach that operators find compelling and easy to deploy, which causes the security technology to be pulled into product. And that's what we need help with. I think that's the end.
Yeah. Hello, I'm Jared Mach, work for Akamai, but I also spent probably about 2 decades running and configuring routers as part of this. And so I have my short list of things, Stuart, here that I've brought up to the mic to make sure that I remember all of them. So, the first thing is, I definitely don't want any of my comments to be construed as a defensive MD5. I was the one who mentioned this morning that, we have BGP sessions that have been up for 5 to 7 years or more, and using that same transport and having that stable is really important. You mentioned the fact that MD5 is the only method that we have to actually secure those sessions. And that was specifically done out of concerns, not just about reset attacks, but about there was a period of time when it was much easier to go and attack the window as well, to go and have some issues there. But when we talk about the router vendors and the implementations that exist there, like tends to not be rekeying support. So I have a full mesh of IBGP sessions with, let's say, 130 or 230 30 devices, and I need to go and change all the, if I need to change the keys on those sessions, I can't just take them all down. It would become a global outage in some cases for many of the networks involved. So we need to have a method to do that. As you mentioned, encryption is not needed. We're not concerned about authenticating the datagram inside of it. We just need to make sure that that transport's reliable. And things like GTSM are helpful because we can use GTSM to go and ensure that at least on a one-hop link, things work. But when we have multi-hop sessions, you mentioned targeted LDP, or if we're doing eBGP multi-hop to either feed information to some third party, we have needs around that allow us to do that. And we may not know the distance across the network for setting the TTL for those sessions.
And it may change.
And it may change. On top of that, we tend to have these routers that come up, as you mentioned, in the cold state, and time is not available. So we can't go and say, oh, well, this key validity starts at this point and moves on to this point, because we can't talk to the NTP server until the routing protocols come up.
Right.
And so, there's a number of interesting dependencies here. One of the most important things here is that most network operators, especially when you talk about edge networks, they don't have any sort of automation or orchestration, which means that they don't have any storage for those keys, which means when they configure them with their transit provider at session turnup, often that person will have left the organization and not have it, and not have those keys, and they end up cutting and pasting them into future devices. And the final comment is the time horizon for any sort of an upgrade here is really out in that 5 to 7 year window. So when we talk about if the IETF says, yes, we want to stop anything from going forward that includes this the current MD5 algorithm, we need to have time as operators to upgrade to something else. And equipment lifecycle is in the 5 to 7 year window, and we may get some software upgrades in there, but in some cases we may not be able to do anything else in there. And so these are some of the key comments I want to make sure that people who are going to come up to the mic behind me as well have in their mind as bounding some of the challenges that we have from an operations perspective of running a network.
Yeah, thank you for re-emphasizing those points. I mean, this is clearly an important question, but we have to understand what space we're working in.
Yeah,
and I'll be looking for some help to make sure those requirements are in any document we write.
Yes, yeah, I have them written down, thankfully.
Thank you.
But yeah, but this is a big concern, because we do need that transport level security, because people do go and point fire hoses and cannons at the routers and play well-formatted BGP messages with the right source ports, et cetera, against the routers, and they do need to be able to survive that type of attack. This has been known to happen in the wild.
Dan Harkins. There seems to be a disconnect here between what you said your problem was and what you're doing, and now your call for help. It seems like the problem is it's the classic security catch-22, where the operators don't want to do anything because the vendors don't support it yet. The vendors aren't going to support it unless the operators demand it. So nothing ever happens. So now you're doing some work in the IETF, and now you're calling for help for a less than Rolls-Royce solution. But even if that did exist, it's not going to break the jam of your security catch-22. So what you should probably do is ask somebody to hack into one of these networks, put the fear of God into the operators, who will then light a fire underneath the vendors.
Well, the way the world is working.
And I'm going to cut the mic line.
Brian Wise, Cisco. First of all, question, Stuart. Your draft and the slides seem to indicate that you're happy with TCP/AO. You just want a new algorithm. Is that really the extent of the changes you're looking for, or are you actually looking for more dramatic?
Well, so if we go with TCP/AO, we need to confirm that this is really the right solution. If we were to go with it, we would need the rekeying stuff to be standardized, which I don't think is done yet. Last time I looked at the spec, it said this is kind of work in progress. And we need an agreement on a common implementation algorithm. Otherwise, people will do different security algorithms, and everyone will fall back to MD5. So we need some agreements as to, and we need the package to be a complete package that operators can turn on and forget.
Okay, so I would just remind, I guess, everyone that TCP/AO was developed for routing protocols, for TCP-based routing protocols. It did take into account many of the requirements that the gentleman from Akamai mentioned, but including the ability to rekey long-lived sessions. It was built with algorithm agility, luckily. Now, the question really is, what is good enough security for TCP/AO, and what are the really blockages with the current default algorithms that are there? So, for example, if we went back to your requirements slide, I would suspect that the using AES CMAC would mostly meet these, including starts up and runs fast in every invocation, because there's an initial key setup like you might have with Flaw. So, if the orchestration of TCP/AO is sufficiently met the requirements, then it really does come down to what are the requirements on the algorithm, and is there really a problem with today's route processors doing AES for TCP? I don't think there is personally, but if there's a difference of opinion in the operations area, then that's something we probably should look into.
Well, we certainly need to be confident that the many generations of route processor can do it, that we will meet in the field can do it. I have no idea. All I know is that whenever I worked for when I worked for an earlier router vendor, the route processors were often Cinderella's children and had rather less CPU and memory than you would have wished.
Mm-hmm. Well, anything new done with algorithms will be on the new route processor. So I think we could
I'm not sure it would. I mean, why so? Because we need to get this deployed network wide. And that means that the old stuff, which is migrating from core to edge and from aggregation to real edge, that needs to be able to take part in the discussion. So I don't know that it's true to say it will all be on a forklift upgrade.
Okay, point taken. Last comment, and I'll sit down, which is, could you please take this to the operations area and have them, if you haven't already, and reinforce the point about demanding from their vendors. That's really the problem here.
So I am pleased to see that the new operations area director is sitting listening.
And coming up to the mic.
Thank you, Ignis.
So just to answer that, the fact that something is standardized and available as an RFC does not necessarily mean that any of the vendors will go and implement that. And this is exactly the case that we have here. There are operational practices and operational hygiene approaches that solve this practical problem to a good enough extent that there's no urgent push from the user community on the vendors to implement that. Certainly, vendors themselves don't see much point, at least at this time, to go proactively and implement that. TCP/AO was when 2006. To my knowledge, there is one commercial implementation of TCP/AO shipping.
Kyle Rose from Akamai. So TCP/AO definitely seems like the obvious choice here from a technical standpoint. I don't want to go too much into the details of that, right? Because there may be some crypto modernization that needs to happen. The original algorithms and whatever the second RFC were. Okay. Right. So HMAC-SHA-1 hasn't actually been broken, but we probably want to not standardize on SHA-1 anyway. But one of the things that I brought up with Jared before when we were talking about this at lunch was you may want to consider, if you're going to do a rev of this protocol, making the protocol itself a little bit more resilient to individual connection breakage. Now, I know that you want to bring down sessions when a connection breaks, right? But you could have two parallel connections, for instance, over the same link. I'm that's just an idea that I'm throwing out there as some way to say, well, if this connection breaks, or if we need to break this connection a la TCP, because we need to rekey with TCP MD5, we could bring one connection down, rotate the key, bring it back up, then bring the other connection down. It's just a thought to come up with some sort of way of making the protocol a little bit more robust to that particular case.
So there's an operator shaking his head there, I can see. Yeah. But if we were to,
maybe you can just straighten it out.
If we were,
Jared will proceed to tell me why I'm wrong.
If we were to do a thing such as that, that is very much in the class of thing where we need help, right? Because we can write routing protocols, at least the authors of the document, are not experts in security protocols.
Right, and I'm not an expert in routing protocols.
So this is a good area, a good case where the two areas need to get together to a common good, or three areas actually, because we need the ops, we need the routing, and we need the security, all to work hand in hand for an optimum solution.
Right, and so for TCP, the reason why I think TCP/AO is a good path to look down is just that it avoids a lot of the bootstrapping issues that some of the more complex protocols have. You know, Jared mentioned about timestamps, right? That would make TLS difficult to use. Also, you know, getting access. You don't want the bootstrapping problem of not being able to get network access to some of the resources you need. Let's say you needed to go forward to an OCSP responder. That wouldn't work.
Yep.
So
we know.
Hi, Eric Criscorla. I was partly responsible for AO, but I'm perfectly happy to concede that it sucks if you say so.
No, I don't know whether it sucks. It's just that it's not been deployed very much, and we get the chance to decide.
Sure, yeah. So I guess what's not entirely clear to me is what, if any, the perceived technical deficiencies are, as opposed to lack of demand. So, like that is to say, so as I understand, as I understand that your survey shows the operators aren't very interested in making it, right? And I guess I'm not quite sure why, like, if the operators just aren't interested because like they're like happy with MD5, which is fine by me, I guess, or if they're not interested because they don't like MD5, but there's something they don't like about AO. And if I understood what that was, maybe we can be more helpful. So I guess. Sure. Well, I guess so. I guess what I don't understand is, like, if we design some other protocol that had different properties, is there some reason to believe? Can I finish? Is there some reason to believe that people would like that better?
Who knows? That's part of the discussion we got to have.
Okay. Well, I'm not. I guess just as a protocol designer, I'm not quite sure what to do.
So nor am I. That's why I'm here. And if it turns out that we've got an impossible problem, we'll write a note and say, please don't revisit LDP security until something or other happens, and we won't keep getting our little protocol enhancements bounced. So I don't care what we do. I just want to do the right thing for the internet.
Hi, Russ Housley. I was security area director at the time TCP/AO was done. And it all started because some guy, Ron Bonica, who came here and said, we have this problem. We need to change keys without tearing the TCP connection down. That led to TCP/AO. Sounds like we're having the same briefing and the same discussion.
So we had already cut the mic line. Sorry, you just got up.
Hi, I'm Jeff Haas. I gave the presentation at IEPG, and no offense to Stuart, this has been presented completely wrong.
Oh, I'm sorry.
Could you please go to the second to last slide on the deck, for my backup material? So the issue that we have here, don't keep going all the way, all the way to one up. There we go. What should we do? So the problem here is not TCP/AO. The issue here, and this is covered in the general presentation, which you can follow here or go listen to the recording from IEPG, is that similar to security people are not routing people are not security people. What you really have with Stuart standing up there, representing the MPLS and other related chairs, is they're not security people. They've been told that as part of their work, security is not adequate in the protocols. It keeps blocking their documents. They need to do something about it. What do they do about it? TCP/AO is a perfectly valid cipher and set of mechanisms to allow them to get their job done. The meta issue that we really have here is we have existing protocols that need to get security bolted on after the fact. You all know in this room that the work is best done up front. So that's one of our problems. The second problem is coming up with a common set of mechanisms in IETF to allow us to get past some of these misunderstandings that we tend to see. So the thing that's in this slide here is really what I'd like to have the group take as action items. We know that transport security considerations have to be discussed up front. This means that we need a little bit of process help to make sure that as new things are being introduced, we take care of that. We also need help for existing mechanisms. In this case, the plea from Stuart, of how do we actually bolt these things on after the fact, ideally without completely having to rewrite the protocol. There's a lot of code that we have to deal with and a lot of operational considerations, not to mention operational and deployment considerations in terms of using the things. It has to work, it has to scale, it has to be usable. The other thing that we could use significant help from here, and this is within your power, similar to what the ops group has done previously for the documents, we could use some common boilerplates for common profiles of how we actually could use security mechanisms such as IPsec, TCP/AO, TLS. Each of these things, depending on the protocol and the mechanism, may be appropriate for our work. But the least efficient way for everyone concerned to actually do this work is for us to have somebody write something down, bring it up to the security group at the very end, and then you say, what the hell were you thinking? So what we'd like to see is ideally a set of common boilerplates, both for new protocols and for existing ones, to say, given the set of properties we need, and we can help you refine the requirements that we need for these types of things, end up with a boilerplate that's appropriate. Obviously, early security review is helpful when it's done at the right spot. We know this is already available to us. A lot of the chairs are not aggressive about seeking it too early. This is something that we probably could do a little bit more chair coordination to take care of. The other thing that we need, and if you scroll back until you see the unicorn, one of the problems that we actually have is that, great, we have this nice, wonderful mechanism out there. Draft Bonica actually solves a lot of this problem. Juniper actually has an early deployment of this. Cisco has a later version of this in the process being deployed. Now, obviously, code can be written, but until we actually have implementations available, it doesn't do any good to boilerplate TCP/AO as the solution if it isn't practically deployed. And that's partially a matter of solving it by encouraging the vendors to go do something about this. A lot of us use stuff that has Linux at the core. If we had somebody that went out to Linux land and were to provide a authenticated, valid, provable TCP/AO implementation, everybody could just lift, we wouldn't be having this conversation next year.
Aaliyah has informed me there is one that's close. I don't know.
The last thing I'm familiar with is a set of patches from 2010. I haven't actually dug into myself. And also emphasized in this deck, one of the conversations that Stephen Farrell and I had over the his term is routing guys are not the security guys in terms of even using security mechanisms. If I can't do a API or a syskettle or something else to actually make use of this as I'm writing stuff, I just want to open up a socket and bang bits. So ideally, these things need to be easy to use. You can't say use TCP/AO and expect me to go write TCP/AO as part of my application.
Rüdiger Volk, Deutsche Telekom. Well, where do I start and where do I end? I have been running around and asking, well, okay, will you do an implementation? I noted the MD5 deprecation thing was out there, and the suggested replacement was defined. And when I'm looking at it right now, this seems to be one of the cases where during the development, some running code, Draft Bonica, was actually produced, but for the final product, it seems not. And delivering a running code years after standardization is kind of not a good way for actually getting things out. And if there is over years no big noise about the missing function, of course one may ask, well, okay, is this really an issue? Being German, I'm kind of trying to do things the right way and maybe more to the letter than is reasonable. So I have been pushing, and after those years, I started to ask, well, okay, should the security guys actually have a look whether under current circumstance, this is really the right thing to do? for getting, and I asked the question once in a while somewhere, and I didn't get good answers. But when I think about what could drive in my environment and a rollout, I would think that kind of complementary functionality that can be rolled out at the same time that gives me overall improvement could be a very important thing. And for me as a BGP interdomain guy, the question would be, well, okay, is there a young model for doing the keychain that seemed to be related to the TCP/AO definition out there? And are we in a state where we would expect that the key management could be done using that, so that we are looking forward as we improve our installations? And for BGP 2, I actually would like very much to inject a link so that the authentication part between the domains could actually be hooked to good stuff that we are having now, which is RPKI, which is supposed to enable authentication between ASs into the game. And if I take that package and have the proof that my management of the whole thing gets easy in a way that is going to work well over the next decade, that would be actually, I think, a fairly good argument.
I'm sorry, the line's closed.
Oh, line's closed.
Yeah.
Thank you.
All right. Yeah. Thank you, Stuart, for coming. I hope you don't feel like you're mauled over by the lions in the lion's den.
Yes. I've certainly had some lions from both sides, but hopefully we can move forward.
Yeah. Hopefully we can get work on actually several things. The boilerplate text and re-reviewing the TCP/AO if it's still right. And maybe some way to convince the operators that they should be caring about this more.
So we have one more. The Yankee store, right?
Yes.
We have the Yankee store. I don't know if it's you. Is it you? Welcome.
Hi there. I'm a new, fresh management AD, and I also have a call for help from the security area. It's about one of the topics that was raised at the NetConf. This is all related to modeling and YANG and configuration. How to approach the configuration aspects of keys, key stores, and crypto configuration in general. I'm relaying the slides. The office and the chairs of the NetConf group were not able to be here. So next, I'll just give a brief overview, skipping through some of the details. What you see here are the slides from a NetConf session, which has way too many details. Problem space. NetConf uses SSH as a transport. RESTConf, the other configuration protocol, uses HTTPS as a transport. There is a need to somehow manage in a centralized way the keys between the agent and the client. And it started as a simple mechanism of storing the SSH host keys. With the RESTConf, the certificate store was added. And one of the problems was that with every possible transport or configuring the configuration domain part, there was a need to have a configuration mechanism for initial transport bootstrap. This model has a lot of history. And next, if you could. Next one, please. The way how current implementations look at that, this model is called the key store, but in fact it doesn't store the keys. It stores the trust anchors, a hierarchy of certificates and other things related to how that can be obtained. Question for the security group here. How much of the configuration work, of the young modeling work that you are doing here depends on the current key store drafts, and whether any of the other young modeling work is being done in an active way? So what I could find out looking through the documents, there was an IPsec young model which expired a couple of years ago, and there's also a couple of documents on the TLS side which are done by the same author from the NetConf working group. Next one, please. There are similar groupings for other objects which are much more advanced in the modeling aspect from routing areas mostly. It's about the interface, it's about the routing types, the network types. Next one, please. So looking into what is in the key store document, it has some groupings for some fragments of the crypto-related configuration elements. Next one, please. Cryptography overall is a big area, and configuration of a cryptography is operationally needed. That's probably only the start of what is covered by those documents. Another question, should this be used as the start, or should it be refactored to something else which is more applicable to the view of the security area, and that it could be used also for NetConf transports too? The next one, please. 3 possible options that the NetConf working group were thinking. Leave it as it is. Use these models only for the NetConf and RESTConf transport, knowing that we intentionally duplicate the configuration. Rename those modules and build, more end-to-end hierarchy. And the main thing is ask advice how to proceed from you. Again, this is a management area, not necessarily having deep insight into the security aspects. Next one, please. That was it. That's it. This is in particular context of the configuration of the security parameters configurations for the NetConf and RESTConf. This does not touch the configuration aspects of security transports in general. No IPsec, no TLS, and other things. That's what I would have. Any questions?
So, hi, Sean Turner. I guess we had an IPsec MIB way back in the day, and that was the one that got done, and then I don't know if it ever got used. To the best of my knowledge, no one has done any kind of Yang for any of this, any stuff that gets done in the security area. I might be getting up and getting corrected here, but I don't think, other than the stuff that Kent did or attempted to, I think really kind of got anywhere.
There is a model expired a couple of years ago, which was an attempt to model IPsec configuration.
Yeah, but it didn't go anywhere.
No.
Hi, Yoav Nir, I'm the chair of I2NSF, and we have a document that provides a data model for IPsec, and it's an active draft in I2NSF.
Okay.
But you're stating no opinion on, splitting the modules or not splitting the modules here?
My name is Michael Richardson. I've tried to use the key store and when it was keychain to model the rekeying of 15.4 networks. It didn't work the way that I wanted it to, and that was fine because it wasn't intended to do that. But I have read it. Kent is also involved in this, I think, right? Yes. So he and I have talked about this a lot, and I think that this is a good approach, a good place to do it. And I don't know what the end game looks like. I think that's maybe a really big question. I think that the ops process will make the animal working group go through and put management stuff, Yang, on a lot of our pieces. It's good to know there's an IPsec Yang model that we can leverage, but this is going to be key for what we're doing, because ultimately we're doing for Bootstrap, we're doing enrollment, and as soon as we have enrollment, we have trust anchors and we have things that need to happen to. So even though I don't know that we want to do updates to it, I'm pretty sure that we want to do monitoring on the objects.
Wes Hardiker, USC. So a long time ago in the same galaxy, we had a IPsec security policy working group that was a partner with the DMTF task force group. I don't remember what the name of it was, to do modeling of IPsec configuration. I'm the author of one of the RFCs that came out of that, out of a few that are missing, that was MIB-based, and the DMTF had this gigantic UML structure kind of thing that took 15 pages printed to be able to actually visibly see the little lines, because the diagram was that complex. You might go look if the DMTF is still using their side of it. From the MIB side of it, I wouldn't recommend you look at that. There was also an RFC that described sort of the architecture, but it ended up being very complex. When you get two standards organizations trying to help each other, it does not go well. But you might see if they're still using it, or if maybe they've simplified their model or something. I haven't looked at the DMTF model in forever. So.
Okay, thanks. So a question then for security ADs. What's your view, and do you see a need for working on Yang models for configuring of the security aspects, especially looking from a routing perspective, tunnels, IPsec tunnels, other type of tunnels, and from a management areas perspective, things that are not automatable, they are questionable from a deployment perspective. Therefore, a large activity that happened in routing area and cooperation of operations area was to develop the core set of modules for configuring at least the basis of the routing. And that is actually in a pretty decent shape now. What is your view on the security manageability from that side?
I mean, I guess we think this is kind of your question. Namely, we're not sure what people want to manage. And so if you want to manage it, it would be good to have a Yang module for that, but I guess we're not really sure how you do that. Right?
Exactly, but writing Yang module it takes two parts. One is a syntax, which is in the management area, and that is done. The other is the subject area, and that needs to be done clearly in those working groups which deal with the protocols. That's how it worked with routing. All of the routing related modules are produced in the relevant routing working groups.
Oh, I see. I don't get the impression there's like a huge amount of enthusiasm for the security protocol designers to design Yang modules for the protocols.
Okay. All right. So this could probably be discussed further. But one thing that I would like to ask from the whole security community is that management people also need help, and explain, or at least guide, how the security related aspects need to be addressed in the modeling.
So Chris Anasio, SACM chair, there's people developing Yang models as part of SACM for what it means to be able to do monitoring and security on network switches, et cetera, within the architecture. Okay. When it matters. And it's not 100% clear that's the tightest fit for working group, but we're allowing the work to progress at this point.
All right, thank you. All right, thanks.
I don't think we have time for a mic, so.
Yeah. Yeah, if no one is running, we have one open mic.
1 minute and a half.
And I have exactly a 20-second question, which is for Stuart's presentation and the discussion about TCP/AO and et cetera. Where is that discussion to happen?
Exactly, yes. No, Deborah's come to save us.
I'm the routing area at AD. So we were just talking in the hallway. Right now it's in the routing area, right? The MPOS and PALS group. But I think the ADs among ops and security are going to discuss this. And possibly we'll even have a design team to help to work on it, that we get this document and more documents jointly among all three of our areas.
Right. All right. There should be one more blue sheet floating around in the back. Please bring that up. And if you have not signed the blue sheets, come up to the front to sign them. I will still bring them up. I can do it. You gotta go. Yeah, but I don't have to. That's true.